Look at ring homomorphism. We have already seen this homomorphism concept in groups. So we know in groups, if we have a function which maps a group under some operation, right? So let me make it as O to another group G prime under a different operation, O prime, right? So in this case, F is a homomorphism if f of x composition y is equal to f of x composition on this side time f of y, right? So we know this. If you want more details, you can look at that particular video. Now, here, remember, for all x comma y belonging to G. So let's extend this concept to rings. What do we get? In rings, remember, we have two operations, right? So let us say a function maps a ring with plus and multiplication to another ring R prime with maybe the same operations or maybe two other operations, some other operation. Then F is called a ring homomorphism if the following is true. So what are the conditions that has to be satisfied? F of x plus y is equal to f of x plus, now this plus is from the codomain, the other ring, plus prime f of y. But since there are two operations, we also have another condition, x times y is equal to f of x times prime f of y. So these are the operations which are coming from the right hand side, and these operations are coming from the left hand side. And here for all x comma y belonging to the first ring. And similarly, as in groups, we have the concept of isomorphism. So F would be a isomorphism if the first condition is what we have already seen, f of x plus y is equal to f of x plus prime f of y, and f of x x times y is equal to f of x times prime f of y. The second condition is, as usual, it should be 1 to 1. That means for every element in the domain in this ring should map to an element in the codomain ring, and it should be on to. That means in R prime there should not be any element left which doesn't map back to an element of R. So these are the three conditions for it to be called an isomorphism. If these two conditions are not satisfied, but the first condition is satisfied, then it is called a ring homomorphism. Okay. So 1 to 1 basically means that if you have f of A is equal to f of B, implies that A is equal to B. F of A and f of B in the R prime, and A and B are in R. And in case of onto, for all x belonging to R prime, there has to be an element y belonging to R such that f of y is equal to x. Now let's look at two examples with respect to homomorphisms. So let us say we have a function which maps the ring of complex numbers with your normal addition and multiplication to a ring of complex numbers again with normal addition and multiplication. Okay, remember this is infinite, just as a interesting point, and this is also infinite. And the function itself, what it does is it takes a complex number and gives us its conjugate. So if you take a complex number here, on this side it will map to its conjugate. So again, let's see how we can say that f is a homomorphism. So let's say instead of saying z, let's actually write it in this form. A plus ib is equal to, when we apply the function, it should give us a minus I, its conjugate. So now let's check the conditions. First one, let's pick up two complex numbers. X is equal to a plus ib and y is equal to c plus id. Okay. Now the first condition says f of x plus y is equal to f of x plus f of y. So let's do the substitutions. Let's continue with LHS and see whether we end up with the right hand side. So f of a plus ib plus c plus id. Now let's first simplify this. We can write it as a plus c, the real parts, plus I times b plus d. And now we actually apply the function. When we apply the function, what does it do? It gives us its conjugate. Its conjugate is what? A plus c minus I times b plus d. Now let's simplify this by opening it up. A plus c minus ib minus id. So what do we get? A minus ib and then minus c time c minus this should be plus c. So plus c minus id. Now a minus ib can be written as f of a plus ib plus c minus id can be written as f of c plus id. So which is equal to the right hand side, or rather what it would be, f of a plus ib plus f of c plus id. Okay, so we have got the addition part done. Now let's look at the second condition. That has to do with the multiplication part. So x times y is equal to f of x times f of y. Again, we'll continue with x equal to a plus ib, y is equal to c plus id. So let's again continue with LHS. F of a plus ib times c plus id. Let's multiply it off within the bracket. So AC plus IAD plus IBC plus I square BD. Now again, we are not applying the function still. We are just simplifying it. So AC minus this will make this minus BD plus I is common, AD plus BC. And now we can apply the function. So what do we get? AC minus BD, the conjugate of this, minus I times AD plus BC. Again now, let's open it up again. AC minus BD minus I AD minus I BC. And now let's see here A is common. So let's take A out and write it as C minus ID, right? And now here In these two cases, B is common. So B times, now here let's take this and this. A is common. So C minus I D. Then B minus B is common here. So B, and this would make this as D minus BD plus IC. Okay. We are in a pickle because here we have C minus ID. Here also we need C minus ID. So how can we convert this D plus IC into C minus ID? So let's see. Let's divide this by I and let's divide this by I. Let's divide both of them by I. Or in other words, let's take I out 1. So this will become D by I plus this will become what? C. But if we take I out, then D by I is nothing but minus D I. And this is plus C, which is nothing but C minus I D. Right? Now here 1 by I is nothing but minus I. So let's rationalize this. We get I by I square, which is equal to I, and I square is minus 1, which is equal to minus I. Right? So that's how minus di came. So which means here what we have to do is A times C minus ID minus I, we have to take it out. So IB times C minus ID. This is the trickiest part. And now this and this is common to both the terms. A minus IB times C minus IB. Now A minus IB is in the second ring. So that means it is a conjugate of something. So we can write it as F of A plus IB times F of C plus ID, which is nothing but our right hand side. Again, I didn't mention the or expanded the or did the necessary substitution. So this would be F of X is F of A plus IB times F of C plus ID. Just substituted X and Y with, so which is the RHS. So therefore both the conditions are satisfied. So we can say F is a homomorphism. Now whether it is a isomorphism or not, you will have to check out whether it is one to one and also on to. Now let's look at another example. So let's look at a mapping of F from the ring of integers to the ring of integer modulo n with, here is the difference, plus addition modulo n and multiplication modulo n, or we can write it as this. Now here again, just for information, this is infinite, but this is going to be finite. Okay, and what does the function do? F of x is equal to x mod n. Okay, let's check whether it is a homomorphism. So let x comma y belongs to z, the ring of integers. Now the first condition says what? That f of x plus y should be equal to f of x addition modulo f of y. Okay. Now let's begin with again LHS. So let's do the substitution. F of x plus y is equal to x plus y modulo n. Now using modular arithmetic, we know this can be written as x mod n plus y mod n, and again we have to do mod n. Why? Because this will give you a number, a particular element of the Zn. This will give you a particular element of Zn. Both of them will be less than n, but if you add them, they may be more than n. So again, to bring it back within Zn, we again do a mod n. So this is equal to x mod n. We are doing this mod n on this. So now this will become addition modulo y mod n. Okay. Now, but x mod n is nothing but f of x addition modulo, and y mod n is nothing but f of y, which is nothing but the RHS. Okay, pretty simple this one, but this was for addition. So similarly, we have to do it for multiplication. So that says f of x times y is equal to f of x times modulo n f of y. So here again, this can be written as x to y mod n, which can be written as x mod n times y mod n. This is modular properties. Okay, and finally mod n, because the product of two Zn elements may go beyond n. Okay, so which once we take care of this mod n, this becomes x mod n multiplication modulo n y mod n, which is equal to, now this is nothing but f of x multiplication modulo n, and this is nothing but f of y, which is nothing but the RHS. So here again, f is a homomorphism. Now in this case, in case of modular arithmetic, remember, in this mapping, it would not be one-to-one, because you get class of elements, right? So multiple elements from Z will map to the same element of Zn. So one thing you need to be very clear about is, when you use the term homomorphism, the context decides whether it is a group homomorphism or the ring homomorphism. So be clear about your context. Most of the times it will be clear if you have a single operation, that means it is, you're talking of a group. Or other way around, if you're talking of a group, there is only a single operation. Whereas in case of a ring, there are two operations. So that's it for now. Bye.